Linear circuits exercises. Hello everyone, welcome to my channel. My name is Rafael. I am an electrical engineer, and this video is going to be a compilation of exam questions on purely resistive linear circuits. We will solve 16 exam questions on a step-by-step manner, so you will be able to understand their solution. Let's go to the first exercise. Exercise number 1. Find the values of I1, I2, and Vx. Okay, my friends, this is the exercise. Let's go to the solution. And to find the value of I1, it is necessary to calculate firstly the equivalent resistance of the circuit. So let's do it. Let's calculate the equivalent resistance of the circuit. The equivalent resistance of the circuit is going to be made up of the parallel combination of these two resistances. They are combined in parallel, and after combining them, we are going to sum with them because this is in series, okay? Plus 10 ohms, okay? Did you understand what I said? We have these two resistances in parallel, and their combination is in series with this. That's why we calculate firstly the parallel equivalent of this, and then we add the 10 ohms resistance. Alright? This is what we are going to do to calculate the equivalent resistance of the circuit. Okay, so the equivalent resistance is going to be, how do we calculate the equivalent resistance of a parallel connection? We multiply them and divide by the sum. Okay? Alright? So, and if we carry out this, we find 16 ohms. This is the equivalent resistance of the circuit. And using the equivalent resistance of the circuit, we can simplify the circuit here. It will be reduced to this. $16 here, 15 volts here, and here I1. Okay? This is how we calculate the current I1, and in this way I1 is equal to the voltage of the voltage source, the voltage of the voltage source, 15 volts, divided by the resistance, 16 ohms. Okay, and this is equal to 0.9375 amps. Alright? And now, going back to the original circuit, we find that, okay, let's go to the original circuit. We are going to return to this circuit here to find Vx. Observe this. Observe that while I1 passes here, there is a voltage drop here, okay? Alright? So Vx, pay attention to this loop here, okay? Vx plus this is equal to 15 volts. This is how we are going to find Vx, okay? So Vx, returning to the original circuit, we understand that Vx plus 10 ohms multiplying I1, we just found the value of I1 is equal to 15 volts, okay? This voltage from here to here and this voltage from here to here is equal to the voltage of the voltage source, okay? Using the value of I1 here, okay? This value here, and passing this to this side, it is going to be 15 volts minus this product here, and we find the value of Vx equal to 5.625 volts. Okay, this is the value of Vx, and this is the value of I1. Lastly, we are going to find the value of I2. Lastly, using the value of Vx, we obtain the value of I2. See that Vx is here, okay? Vx is here. Vx is both on top of this resistor and this resistor, okay? So I2 is equal to Vx divided by 12 ohms, alright? It is easy, it is simple. Vx is not only on top of this resistor here. Vx is here on top of this, and I2 goes to this resistor here. And the Vx divided by 12 ohms is equal to the value of Vx we just calculated. It is 5.625 volts divided by 12 ohms, and then ultimately we conclude the exercise by finding that the value of I2 is 0.468 amps. Okay, my friends, and this is all the exercise requested of us: the value of I1, the value of Vx, and the value of I2. And this is all for exercise 1. Let's go to exercise 2. Exercise number 2 now. For the circuit of the figure, find the values of I1, I2, and the power for each circuit element, and state whether each is absorbing or delivering energy. Okay, my friends, this is exercise number 2. Let's go to the solution. And to find what is being asked, we will use the nodal rule. That is, the sum of the currents that enter a node is equal to the sum of the currents that leave the node. Alright, this is a node here, okay? And what is the current that is entering the node? 6 amps. 6 amps is entering the node. And what are the currents that leave the node? The currents that leave the node are I1, I2, and 8 amps. Okay, so this is the nodal rule, alright? The sum of the currents that enter the node has to be equal to the sum of the currents that leave the node. Alright, my friends, this is what we are working with, and now we are going to write I1 and I2 in terms of Vx, okay? It is way we say that 6 amps is equal to Vx divided by 5 ohms plus Vx divided by 15 ohms plus 8 amps, okay? Because I1 is equal to the voltage divided by the resistance, alright? Vx divided by 5 ohms. And I2 is equally written in this way: the voltage divided by the resistance. Alright, then it is Vx divided by 15 ohms, and this current here, we already know it is 8 amps. Alright, my friends, this is the nodal rule that will enable us calculate what the exercise wants us to calculate. Okay, so here I'm gonna pass this current to this side. It becomes 6 amps minus 8 amps equal to Vx 1 over 5 plus 1 over 15. Okay, now it's just mathematics. And if we manipulate this, let's manipulate this. 6 minus 8 is negative 2. Here we are going to take this 15 here to calculate this in this way here. Okay, Vx is going to be equal to 15. 15 divided by 5 is 3, plus 15 divided by 15 is 1. Okay, and this is equal to Vx multiplying 4 over 15. Okay, this is just mathematics, and we find that negative 2 amps is equal to Vx 4 over 15. And ultimately, we find that Vx is equal to negative 7.5 volts. I'm going to write it here because I'm going to need space. Then, just to save the result here, Vx is equal to negative 7.5 volts. Okay, my friends, I'm going to erase here because I'm going to need some room for more calculation. Okay, now we want to find the value of I1. With the value of Vx that we just found, we can find the value of I1, which is Vx divided by 5 ohms, and this is equal to negative 7.5 volts divided by 5 ohms, and this is equal to negative 1.5 amps. Okay, so what does it mean? We found a negative number here. What does it mean? It is wrong? No, it is not wrong. It means that instead of going down here, actually I1 is going upwards. This is what this negative sign means, okay? If we found a positive sign here, it would mean that precisely I1 is going downwards here. But as we found a negative sign, it means that I1 is going in the reverse direction. Alright, now let's do the same for I2. Likewise, we calculate I2 by dividing the voltage by the resistance. Vx, we know it is negative 7.5 volts, and the resistance 15 ohms, and we find that I2 is negative 0.5 amps. And again, this negative sign here means that the current is going upwards instead of downwards. Alright, my friends, and we are almost over. What we need to do now is to state whether they are absorbing or delivering energy. For the 6 amp source, we want to calculate the power, and the power is simply the current times the voltage, and the voltage is 7.5 volts. We are working here only with the magnitude of the voltage, never mind the sign, only the magnitude of the voltage, and we find 45 watts. Okay, my friends, and this is absorbing, okay, this is absorbing. This has to be absorbing because 8 amps is greater than 6 amps. Then this is absorbing from this. Alright, and now let's go to the other 8 amps source. Okay, it's gonna be 8 amps times 7.5 volts, and this is equal to 60 watts. And this source here is actually delivering energy. Alright, and how about the 5 ohms resistor? the 5 ohms resistor. The 5 ohm resistor, the power is going to be the voltage squared 7.5 squared divided by the resistance of the resistor, which is 5 ohms, and this is equal to 11.25 watts. And obviously, as a passive element, a resistor is absorbing energy. And finally, for the 15 ohms resistor, again, the power is calculated in this way, and this is equal to 3.75 watts. And again, as a passive element, a resistor is obviously absorbing energy. Okay, my friends, and this is all for exercise number 2. Let's go to exercise number 3. Exercise number 3 now. Find the voltages V1 and V2 for the circuit on the board. Alright, my friends, this is exercise number 3. Let's go to the solution. Okay, my friends? And how are we going to calculate this? The strategy that we will use is to combine resistances in series and parallel until the circuit becomes an equivalent resistance across the voltage source. Alright, let's begin with equivalent resistance number 1. Equivalent resistance number 1 is going to be the combination between these 5 ohms and these 25 ohms. They are in series, isn't it? So 25 plus 5 is 30 ohms. Okay? And we replace these two by 30 ohms. And this 30 ohms is going to be in parallel with this 30 ohms here. Then equivalent resistance number 2 is going to be the parallel combination between this resistance here, 30 ohms, in parallel with this resistance here. And how do we calculate the parallel combination of two resistance? It's the product over the sum, okay? And this is equal to 15 ohms. Alright, my friends, and we replace all these by 15 ohms, and this 15 ohms is going to be in series, in parallel with this 10 ohms. Okay, so equivalent resistance number 3 is going to be the parallel connection between this 10 ohms and this 15 ohms. And this is solved by computing the product over the sum. Okay, and this is equal to 6 ohms. Okay, my friends, now we have reduced the circuit to something that is easier to work with. Okay, let's remember this, and we are going to rewrite the circuit in a simpler way. The circuit is going to be this. Okay, I have here the voltage source, there 12 ohms, here 6 ohms, and the equivalent resistance that we just found, which is 6 ohms. Okay, it's 6 ohms here, and this is V1, and this is 12 ohms, this is 6 ohms, and this is the voltage of the source, 12 volts. Okay, and we can calculate using a current. I'm gonna call it Ix here. all right, just to help us calculate. Ix is equal to 12 volts divided by 6 plus 6, 12, plus 12, 24. 24 ohms. And this is 0.5 amps. Okay, this is the value of Ix. And if we multiply Ix by 6 ohms, we find V1. V1 is equal to 6 ohms times 0.5 amps, which is equal to 3 volts. Okay? The value of V1 is 3 volts. Alright, my friends? This is how we calculate. One more time, I'm going to repeat so you will understand everything. We combined this resistance with this resistance. 5 plus 25 is 30. And we combined this with this in parallel. 30 with 30 in parallel is 15. And we combined with this 10 in parallel. 15 with 10 in parallel is 6. Okay, and the voltage V1 will be on top of 6 ohms. We computed Ix by dividing 12 volts by 24 ohms, and we found a current of 0.5 amps. 6 ohms times 0.5 amps is 3 volts, and this is the value of V1. Now we can calculate the value of V2 by using the value of V1. I have here V1, okay, here 25 ohms, and here 5 ohms, and here V2, okay? And from the value of V1, we can calculate the value of V2 by applying a voltage divider. Alright, so V2 is going to be 5 divided by 5 plus 25 times the value of V1, which is 3 volts, and this is equal to 0.5 volts. Okay, my friends, this is the value of V1, and this is the value of V2, and this is all the exercise wanted from us. Alright, I hope you understood everything. Let's move on to exercise 4. Okay, my friends, let's go to exercise number 4 now. Find the values of Vs, V1, and I2 for the circuit of the figure. Okay, my friends, this is the exercise. Let's go to the solution. And the first step that we are going to take is to calculate the equivalent resistance seen by this source here. Okay? And the first equivalent resistance is going to be the combination between this and these resistances. Okay, so equivalent resistance number 1 is going to be the series connection between 25 ohms and 5 ohms, and this is equal to 30 ohms. Alright? And this 30 ohms that replaces this is going to be in parallel with this 20 ohms. So the equivalent resistance number 2 is going to be the parallel connection between 20 ohms and 30 ohms. And this is equal to the product divided by the sum. Okay, my friends? And this is equal to 12 ohms. Alright? And this 12 ohms replaces all this. And observe that this 12 ohms is in series with this 6 ohms. And the total equivalent resistance is therefore 6 ohms plus 12 ohms, which is 18 ohms. Okay? We have calculated the equivalent resistance, and we've reduced the circuit to this. There is going to be a source here. Okay? And a resistance here. This resistance we calculated and we found 18 ohms, here 3 amps, and there will be a voltage Vs here. The value of Vs can be immediately found by multiplying 3 amps by 18 ohms, and Vs is equal to 54 volts. Okay, my friends? And if we return to the original circuit, we can calculate the value of V1. Observe that 3 amps flows in this direction here, okay? Whenever we have a current source, the current of the current source is the only current that flows in its own branch, okay? So we know that the current that flows through this 6 ohms resistor is 3 amps. There is going to be a voltage drop here, and from this point to this point there is a voltage drop. From this point to this point there is a voltage drop, and this plus this is equal to Vs, okay? So what we understood is that Vs is equal to 6 ohms times 3 amps plus V1. But we already know the value of Vs. The value of Vs we just calculated it there, and it is 54 volts, okay? We are going to multiply this, pass to the other side, and we find that V1 is equal to 36 volts. Okay, my friends? The value of V1 is 36 volts. And with the value of V1, we can calculate I2 and V2. I'm going to erase here for some room, and we are going to calculate what's left for us to calculate, okay? And we can forget this part here. It doesn't matter what's at the left. We simply do this. We already know V1. We already know V1, and here 25 ohms, and here 5 ohms. There is a current here, I2, and there is a voltage drop here. We call it V2, okay? And to find V2, we simply apply the voltage divider. V2 is equal to 5 divided by 5 plus 25 times the value of V1, and the value of V1 we found it to be 36 volts, and if we compute this we find a value of 6 volts for voltage V2, and if we divide V2 by 5 ohms, V2 divided by 5 ohms we find I2, okay, and V2 is 6 volts divided by 5 ohms, and this is equal to 1.2 amps, my friends, and this is all the exercise requested of us. Alright, my friends, and I hope you've understood everything. Let's move on to the other exercise, to exercise number 5. Exercise number 5 now. Find the voltage V and the currents I1 and I2 for the circuit on the board. Alright, my friends, this is what the exercise wants us to calculate, and this is what we are going to do. And as we did before in the previous exercise, we are going to combine resistances in series and in parallel. Let's begin with this combination here. We are going to combine them, and we are going to call equivalent resistance number 1, which is the parallel connection between 18 ohms and 9 ohms, okay? And when combining resistances in parallel, we do the following. It is the product divided by the sum, okay? And the result is 6 ohms, okay? Now let's do the same for this group here, this couple of resistance here. We're gonna call it equivalent resistance number 2, and it is going to be the parallel connection between 10 ohms and 40 ohms, and as we know, it is the product over the sum, and this is equal to 8 ohms, okay? This 6 ohms replaces this, and this 8 ohms replaces this. And observe that they are in series with this 6 ohms resistance, and the total equivalent resistance is going to be this 6, which replaces this, plus this 8, which replaces this, plus this 6 ohms, and this is equal to 20 ohms, okay? And we are going to use this. We are going to use the equivalent resistance that we just found. Now that we know the total equivalent resistance, we can find the value of V. Let's understand the circuit in this way here, okay? The total equivalent resistance we just calculated, and we found 20 ohms. Here we have 5 amps, and the voltage is here, okay? And we can immediately find the value of V by simply multiplying 5 amps by 20 ohms, and this is equal to 100 volts. Alright, this is the value of V, 100 volts. Okay, my friends, and now let me raise here for some room, and we are going to calculate the other parameters that the exercise wanted us to calculate. Observe that we have here the current source, okay, here the equivalent resistance that replaced this, and it is 6 ohms. There is this 6 ohms here, 6 ohms, and the equivalent resistance that replaced this, and we found it to be 8 ohms, okay? And observe that we have here 100, we just found this 100 volts, and as the current, observe that the current flows in this way here, okay? Alright, observe that the current of the current source flows in this way here. Then there is going to be a voltage drop here, a voltage drop here, and a voltage drop here, okay? We're gonna call it here V1, V2, V3, okay? So, what are we understanding here, alright? What are we understanding? We are understanding that 100 volts is equal to V1 plus V2 plus V3, okay? Alright? Did you guys understand it? Did you guys understand it? The current is flowing in this direction here, then there is going to be a voltage drop here, here, and here. And the sum of these voltage drops, V1, which is from here to here, V2, which is from here to here, and V3, which is from here to here, has to be equal to 100 volts. Okay, my friends? And how do we calculate this? We are going to calculate V1 first. V1 is going to be equal to 5 amps. Okay, the current that flows here is 5 amps times the value of the resistance, which is 8 ohms, and this is equal to 40 volts. Okay? Likewise, for V2, we know that the voltage V2 is going to be equal to the voltage V3 because it is the same resistance and the same current V3, and this is equal to 6 ohms times 3 times 5 amps, and this is equal to 30 volts. Okay, my friends, and now we are going to return to the original circuit. Okay, we're gonna have here this voltage here, V1, and we're gonna have here this voltage here, which we call V3. Okay, we just calculated the V1 and we calculated the V3. Okay, so I1, sorry, I made a mistake here. The polarity is inverse. Okay, V1 is not like this. Okay, V1 is like this. V1 is pointing downwards and V3 pointing upwards. All right, so I1 is going to be equal to V1 divided by 10 ohms, and this is equal to 40 volts divided by 10 ohms, which is 4 amps. Okay, observe the polarity of V1. V1 is not pointing upwards as we understood here because of the way the current flows. Okay, it depends on the way the current flows. Because of the way the current flows, V1 is not pointing upwards, V1 is pointing downwards here. Okay, and to calculate the value of I2, we simply divide V3 by 9 ohms, and this is equal to 30 volts divided by 9 ohms, and this is equal to 3.333 amps. Okay, my friends, and this is all the exercise requested of us, and I hope you have understood everything. Let's move on to the next exercise. Let's go to exercise number 6. Let's go to exercise 6, my friends. Consider the circuit of the figure. With the switch open, the value of V2 is 10 volts. On the other hand, with the switch closed, the value of V2 is 8 volts. With this data, determine the values of R2 and RL. Alright, my friends, this is the exercise. Let's go to the solution and let's begin with the situation in which the switch is open. Switch open, and when the switch is open, the exercise says that the value of V2 is equal to 10 volts. Okay, my friends, the switch open, this part of the circuit doesn't participate because there is no current flowing in that direction. Alright, then the current I1 is going to flow here. Alright, and we can find the value of I1 by simply doing this. I1 is going to be equal to 16 volts divided by 6 ohms plus R2. Okay, and we can also say that V2 can be calculated by applying the voltage divider, and V2 is going to be equal to R2 divided by 6 ohms plus R2 times the value of the voltage source, which is 16 volts. Okay, my friends, and we know the exercise gave us this value. We know that V2 is equal to 10 volts. Then we use the value of 10 volts here. 10 volts is going to be equal to R2 divided by 6 plus R2 times 16 volts. Okay, and manipulating this, okay, we are going to carry out an algebraic manipulation here. I invite you to try in your house. Manipulating this, we find that R2 is equal to 10 ohms. Okay, my friends, and this is how we find R2. And if we are interested in calculating, we can use the value of R2 here to calculate I1. It is going to be 16 volts divided by 6 plus 10, 16 ohms, and this is 1 amp. When the switch is open, only in the case when the switch is open, the current is 1 amp, and the value of the resistance in all cases, both closed and open, when the switch is open, this is what I wanted to say. When the switch is open, only in the case when the switch is open, the value of I1 is 1 amp. But in both cases, when the switch is closed or open, the value of R2 is 10 ohms. Okay, my friends, now let's work with the second case, the case in which the switch is closed. Let me erase here for some room for the next calculation. Okay, let's analyze the case in which the switch is closed. When the switch is closed, the exercises say that the value of V2 is 8 volts, okay? And in this way, we have here this. The switch is going to be closed, okay? V2 is 8 volts. Let's inspect this. Let's call here I2, and let's call here I3, and apply nodal rule. Alright? And what does the nodal rule say? The nodal rule says that the sum of the currents that enter a node is equal to the sum of the currents that leave a node. Alright? And in this way, I1 is going to be equal to I2 plus I3, okay? Why? Because I1 is the only current entering the node, and I2 and I3 are the currents that are leaving the node, alright? And we are going to substitute here and write I1 in terms of the voltage drops, okay? We already know that V2 is equal to 8 volts because the exercise imposed this condition. When the switch is closed, V2 has to be equal to 8 volts. Then I1 is going to be equal to 16 volts minus 8 volts. 16 volts minus 8 volts divided by 6 ohms. And I2, who is I2? I2 is 8 volts divided by R2. Okay, we don't know the value of R2. Yes, we know, we calculated in the first step, we calculated it to be 10 ohms. Then we substitute it to be 10 ohms. And here we are going to find the value of RL. V2 divided by RL. Okay, my friends? And we are going to manipulate this. 16 volts minus 8 volts is 8 volts. 8 volts divided by 6 ohms. And this is going to be 8 volts divided by 10 ohms. 8 volts divided by 10 ohms is 0.8 amps plus 8 volts divided by RL. Okay, and we are going to carry out this algebraic manipulation. I invite you to try in your house. It is very easy, and in this way we find that RL is equal to 15 ohms. Okay, my friends, this is the answer of exercise number 6. Let's go to exercise number 7 now. Let's go to exercise 7, my friends. Use the current division principle to calculate the values of I1 and I2. Alright, this is what we are going to do. But before doing this, before using the current division principle, we are going to use some introductory concepts to understand what's going to happen. Alright, for any given node, the sum of the currents that enter the node is equal to the sum of the currents that leave the node. Alright, so for the node Vx, the sum of the currents that enter the node has to be equal to the sum of the currents that leave the node. What is the current that enters the node? 5 amps. And what are the currents that leave the node? I1 and I2. Okay, so in accordance with the nodal rule, the sum of the currents that enter the node, 5 amps, has to be equal to the sum of the currents that leave the node, I1 plus I2. Alright, and let's write I1 and I2 in terms of Vx. Okay, so 5 amps is going to be equal to I1, but I1 is equal to Vx divided by R1. Alright? And how about I2? I2 is equal to Vx divided by R2. Okay? And with substitute, it is going to be Vx divided by 12 ohms plus Vx divided by 8 ohms. Okay? And now it is it's just mathematics. It's just mathematics, some algebraic manipulations here that we are going to use. Okay, it is going to be Vx 1 over 12 plus 1 over 8. And if you carry out this algebraic manipulation, you're going to find that Vx is equal to 24 volts. Okay, my friends, for the parallel connection between these two resistances here, let's combine them, okay? Let's combine these two resistances in parallel to see what's going to happen. Okay, the equivalent resistance is going to be equal to R1 in parallel to R2, and this is equal to R1 times R2 divided by R1 plus R2, okay? Substituting the values R1 12 and R2 8, we find the value of the equivalent resistance. Alright, but we are not going to worry with this now. We are going to calculate this later. Okay, and using the equivalent resistance, we find this. Alright, this is the equivalent resistance here, and the voltage drop Vx is here. This is 5 amps. Okay, the current here is the current that's going to flow here. Okay, my friends, and the value of Vx. We have already calculated the value of Vx. The value of Vx is equal to 24 volts, and the value of observe this, it is important to observe this. Observe that Vx is equal to 5 amps. Okay, we are looking at this now. Observe that Vx is equal to 5 amps times the parallel connection. The equivalent resistance is equal to the parallel connection, which is R1 times R2 divided by R1 plus R2. Okay, my friends, we are understanding how to come up with the current divider. Alright, we don't yet know how to implement the current divider. We are using these steps here to understand how to use the current divider. And observe here, looking back to the original circuit, observe that I1 is equal to Vx divided by R1, okay? Alright? Isn't it? But Vx is this, okay? So it is going to be 1 over R1 times 5 amps R1 times R2 divided by R1 plus R2, okay? Okay? And we can simplify this, we can cut this with this, okay? And in this way, I1 is equal to 5 amps times R2 divided by R1 plus R2. Okay, my friends, this is how we use the current divider. Alright? I followed these steps here just to demonstrate to you how we come up with the expression of the current divider. Now that we know this, we can simply use. Let's use the current divider then. Using the expression that I just demonstrated to you, we can find that I1 is equal to 5 amps times R2 divided by R1 plus R2. And likewise, I2 is going to be equal to 5 amps times R1 divided by R1 plus R2. What we need to do is to simply use the values. We need to substitute the values to find, okay, I1 is going to be equal to 5 amps times R2 is 8 ohms, 12 ohms plus 8 ohms, and this is equal to 2 amps. Similarly, we calculate here and we substitute the values. Alright, R1 is 12 ohms and 12 ohms plus 8 ohms. We calculate this and we find that I2 is equal to 3 amps. Okay, my friends, this is the expression of the current divider. Alright, I have a voltage source. Let's say I is the current of the current source, and if I want to calculate I1 is going to be equal to R2 divided by R1 plus R2, and for I2 I calculate I, which is the current of the current source, times R1 divided by R1 plus R2. Okay, we could just use the formulas, but instead of memorizing them, I decided to demonstrate how they originate before using them, and this is what I did, my friends. Alright, this is all for exercise 7. Let's go to exercise 8 now. Alright, my friends, let's go to exercise 8. The exercise wants us to use the voltage division principle to calculate the value of V. Okay, V is this voltage here. Okay, and this is the exercise. Let's go to the solution. But before solving, let's observe that V is on top of both R2 and R3. Okay. Then we must work with the equivalent resistance. We need to work with the equivalent resistance between R2 and R3, alright? Then the equivalent resistance is going to be equal to the parallel connection between R2 and R3. And as we already saw, it is the product over the sum. Okay? And substituting the values, it is 20 and 20, 20 times 20 divided by 20 plus 20, and this is equal to 10 ohms. Okay, my friends? And in this way, we reduce the circuit to this. The resistance R1 here, the equivalent resistance we just calculated, and here the voltage source. Alright, 10 volts. Okay, this is R1, this is the equivalent resistance, and observe that we could not use the value of R2 or the value of R3 alone, because V is not only on top of R2 or R3, V is on top of both. That's why we needed to calculate the equivalent resistance. Okay, this is going to be V. Alright, and we are going to apply the voltage division principle here to calculate the value of V. Then V is going to be equal to the equivalent resistance divided by R1 plus the equivalent resistance times the value of the voltage source, 10 volts. Okay, my friends? And let's substitute. V is going to be equal to 10. 10 divided by R1 is 20, and the equivalent resistance 10, and this multiplies 10 volts. Okay, my friends? And if you conduct this, it is going to be 10 divided by 30 times 10, and this is equal to 3.333 volts. Alright, my friends, this is how we solve exercise number 8. Let's go ahead and go to exercise number 9. Let's go to exercise 9, my friends. For the circuit of the figure, solve for the node voltages and find the value of I1. The exercise wants us to calculate the value of V1, V2, and the value of I1, my friends, and this is exactly what we are going to do. Okay, and we are going to use the nodal rule here to calculate everything. And the nodal rule says that the sum of the currents that enter a node is equal to the sum of the currents that leave a node. Alright, my friends, let's work with node 1 first. What are the currents that enter the node? The current that is entering the node is only this, 1 amp. And what are the currents that leave the node? The currents leaving the node is I2 and I1. Then we write I2 plus I1. Okay, my friends? One more time, the sum of the currents that enter the node has to be equal to the sum of the currents that leave the node. Okay? We are going to write this expression in terms of voltage drops and resistances. Then I2 becomes V1 divided by 20 ohms, okay? Isn't it? I2 is the division between the voltage and the resistance of this resistor here. And how about I1? I1 is going to be equal to V1 minus V2 divided by 10 ohms. Okay, my friends? And this is the first expression, the expression of node 1. Let's store it here because we are going to need space. Then 1 amp is equal to V1 over 20 ohms plus V1 minus V2 divided by 10 ohms. Okay, this is the equation for node 1. Let's work now on node 2. Now node 2. Node 2, let's apply the nodal rule and understand the currents that enter the node and the currents that leave the node. One more time, we have to bear in mind that the sum of the currents that enter a node is equal to the sum of the currents that leave the node. What are the currents that enter the node? I1 and 2 amps. Then we write I1 plus 2 amps. And what is the current that is leaving the node? I3. Then it is equal to I3. Alright, my friends? And instead of letting it the way it is, we are going to write it in terms of voltages and resistances. I1 is V1 minus V2 divided by 10 ohms plus 2 amps. And how do we write I3? I3 is V2 divided by 5 ohms. Okay, my friends? This is the expression for node 2. We are going to store it here because we are going to need space here. It is V1 minus V2 divided by 10 plus 2 amps, which is equal to V2 divided by 5. Alright, this is the expression for node 2. Now we are going to manipulate, okay? We are going to manipulate these expressions to find the values of the voltages. Let's work on the first. 1 amp has to be equal to V1 divided by 20 plus V1 divided by 10 minus V2 divided by 10, okay? We are going to manipulate this, and we're going to find ultimately that 20 volts plus 2 times V2 is equal to 3 times V1, okay? This is easy. I invite you to try it in your house. It is easy. We are going to do the same for the second equation that represents node 2. It is V1 divided by 10 minus V2 divided by 10 plus 2 equal to V2 divided by 5. Okay, we are going to manipulate this as well, and we are going to find that 20 volts is equal to 3 times V2 minus V1. Alright, my friends, these are the expressions that we are working with, and from here we can immediately see that V1, I pass negative V1 to this side, I let it here 3V2 minus 20 volts. Okay, my friends? And this is the value of V1 in terms of V2. We are going to use this here, okay? Then 20 volts plus 2 times V2 is equal to 3 times V1. But V1 is 3 V2 minus 20 volts. Okay, my friends? And from this, I have only V2 here, okay, only one variable. And if I solve this equation, I find that V2 is equal to 11.43 volts. Okay, my friends? And now I am going to use this here to find the value of V1. V1 is going to therefore be 3 times 11.43 minus 20 volts, and then I find the value of 14.29 volts for V1, okay? This is what the exercise wanted us to calculate, the values of the voltages at the nodes. And lastly, the exercise wants us to calculate the value of I1. If we have V1 and V2, we can calculate I1. I1 is going to be equal to V1 minus V2 divided by 10 ohms, and we simply use the values. V1 is 14.29 volts, V2 is, where is V2? V2 is 11.43 volts, and we divide by 10 ohms, and consequently we find 0.286 amps. Okay, my friends, and this is all the exercise requested from us, and I hope you have understood everything. If not, return to the beginning of the video and watch it again. Okay, my friends, let's move on and go to exercise number 10. Let's go to a similar exercise. Let's go to exercise number 10. Solve for the value of the node voltages and find the value of Ix. The node voltages that the exercise is referring to is V1 and V2. Okay, my friends, and this is the exercise. Let's go to the solution. Applying the nodal rule at node 1, okay, let's regard this as node 1. Okay, applying the nodal rule at node 1, and bearing in mind that the sum of the currents that enter the node is equal to the sum of the currents that leave the node, we know that the current entering the node is 1 amp. And what are the currents? What are the currents that leave the node? We have two currents leaving the node, I1 and Ix. I1 plus Ix. Okay, this is the equation for node 1, but we are not going to let it the way it is because we don't know the values of the currents. We have to write them in terms of voltage and resistance. How do I write I1? I1 can be written as V1 divided by 10 ohms. Okay? Isn't it? And how about Ix? Ix is equal to V1 minus V2 divided by 5 ohms. Okay, my friends, this is the equation for node 1, and we are going to manipulate it. Okay, as we did in the previous exercise, we are going to manipulate this, and we are going to do as follows: V1 divided by 10 plus V1 divided by 5 minus V2 divided by 5, just separating the terms, and after manipulating we find that 10 volts is equal to 3 times V1 minus 2 times V2. Okay, this is the equation representing the equation for node 1. Let's do the same for node 2. Node 2, okay? What are the currents that enter the node? There is only one current entering the node. It is Ix. Ix is equal to, what are the currents leaving the node? This, the current of this controlled source, and I3. Then it is 0.5 Ix plus I3. Okay, my friends, this is the equation representing node 2. Ix can be written as we did before, V1 minus V2 divided by 5 ohms is going to be equal to 0.5 Ix plus I3, and I3 is equal to V2 divided by 20 ohms, alright? And we are going to manipulate this in order to find a simpler equation. We are going to separate here V1 divided by 5 minus V2 divided by 5 equal to 0.5 Ix plus V2 divided by 20. Okay, and after manipulating, we find that 10 Ix is going to be equal to 4 V1 minus 5 V2. Okay, these are the two equations that we are working with. We are going to use these two equations here to solve this exercise. Alright, my friends, I'm going to erase here because I'm going to need some room. Save these two equations here because they are important and we are going to use them. Alright, I need to clear the board because I need space. Alright, observe that Ix is equal to V1 minus V2 divided by 5. Okay? Alright? It is easy to understand this. This minus this divided by 5 is Ix. And in this way, returning to one of the equations, I had written here this 10 times Ix is equal to 4 times V1 minus 5 times V2, okay? I had written this equation there, and we are going to use that Ix is equal to V1 minus V2 divided by 5 ohms. Then 10 times V1 minus V2 divided by 5 is equal to 4 times V1 minus 5 times V2. Okay? This is the way we can use to eliminate this Ix here, because we have two equations with 3 variables. We cannot solve such an equation. We need to have 2 variables for 2 equations in order for them to be solvable. Okay? And after manipulating this, we find that V1 is equal to 3/halves of V2. Okay? And we are going to apply this in the other equation. I asked you to keep the equation. I had to erase because I needed room. Then the equation is 10 volts is equal to 3 times, let me check here, 3 times V1, but V1 is 3/2 of V2 minus 2 times V2, okay? And in this way, we find that V2 is equal to 4 volts, and V1 is equal to 6 volts. Okay, my friends, working on these equations, we find that V2 is 4 volts and V1 is 6 volts. Alright, my friends, and now it is straightforward. We can calculate the value of Ix. Ix is equal to V1 minus V2 divided by 5 ohms, and this is equal to 6 volts minus 4 volts divided by 5 ohms, and this is equal to 0.5 amps. Okay, my friends, this is the value of Ix, and this is all the exercise wanted from us. And let's move on. Let's move on to the next exercise. Let's go to exercise 11. Exercise 11, my friends, it looks a little bit harder than the others, but you're gonna see it is not. Find the values of V1 and V2 in the following circuit. Okay, my friends, this is the circuit that we are going to work with, and we are going to need to calculate, as the exercise requested, the values of V1 and V2, okay? And we are going to use the nodal rule. Let's call this node here node 1, and let's call this node here node 2. Let's apply the nodal rule firstly on node 1, okay? Let's say that there is this current entering here, and this current leaving here, and leaving here, and leaving here, okay? And in this way, the sum of the currents that enter a node has to be equal to the sum of the currents that leave a node. Alright? Then the current that enters the node is 1 amp. And how about the currents that leave the node? We have this current here. Let's work on this current here first. It is gonna be V1 divided by 5 ohms, and this current here, it is gonna be V1 minus Vy divided by 15 ohms. And how about this current here? It is gonna be V1 minus V2 divided by 10 ohms, okay? And observe that V1 minus V2 is equal to Vx, okay? That is this voltage here, Vx, that we are going to need to use because we have a controlled source here that is controlled by this voltage, all right? So this is what we are going to do, my friends. And observe that Vy is this, okay? Vy is this. Vy is equal to 2 times Vx, okay? And Vx is this, V1 minus V2, then Vy is equal to 2 times V1 minus V2, all right? This is what we are going to do to calculate everything. And we have to separate the terms here. It is going to be 1 amp equal to negative Vx over 10 ohms plus V1 over 5 ohms plus V1 over 15 ohms minus 2 times Vx divided by 15 ohms. Okay, my friends, this is the manipulation, the step that we take from this to here using this, okay, substituting here Vy by this. All right, my friends, and manipulating, we find that this is equal to, I'm going to store it here. I'm going to store it here because it is important. Our first result, 30 volts, is equal to 15 V1 minus 7 V2. Okay? This is the equation that we got from analyzing node 1. We are going to analyze node 2 now and find another equation. Okay? Node 2 now. Node 2. Okay? For node 2, what are the currents entering node 2? We have these currents here entering node 2. There is going to be a current entering node 2 here, another current entering node 2 here, and this current here also enters node 2, and the only current that leaves node 2 is that current there. We are going to apply the nodal rule, bearing in mind that the sum of the currents that enter a node have to be equal to the sum of the currents that leave a node, okay? Then the currents that enter the node, 2 amps, is the current entering the node. And this current here also enters the node. This is equal to Vy minus V2 divided by 10 ohms, and this current here also enters the node. This is equal to V1 minus V2 divided by 10 ohms, and the only current that leaves the node is this, and it has to be equal to V2 divided by 5 ohms. Okay, my friends, we are going to have to manipulate this, and we are going to bear in mind again, we're going to use this, that V1 minus V2 is equal to Vx, okay? V1 minus V2 is equal to Vx. We need to know this Vx because we have a controlled source here, controlled by the value of Vx. Then Vy is equal to 2 times Vx, and this is equal to 2 times Vx is V1 minus V2, okay? we are going to use this here to manipulate the equation, and I invite you to try to manipulate the equation. Alright, it is easy, it's simple mathematics. You simply use this, and you're gonna find that I'm gonna store it here, okay, because it is the result of the analysis of node 2, and it is V1 plus 2 times V2 is equal to 20 volts. Okay, my friends, now that we have these two equations, we can calculate what we want. All right, observe here that V1 is equal to 20 volts minus 2 times V2, okay? And if we use the value, the expression for V1 here, we find that 30 volts is equal to 15 times V1, but V1 is 20 volts minus 2 times V2 minus 7 times V2, okay? This is the manipulation that we are going to use to find the values of both V1 and V2, and in this way we find that V2 is equal to 7.297 volts, okay? And now it is easy to find the value of V1. We take this value and substitute here. We find that V1 is equal to 20 volts minus 2 times 7.297 volts. And ultimately, we find that V1 is equal to 5.406 volts. Okay, my friends, this is the result of exercise 11. Exercise 11, let me refresh my mind. Exercise 11 wanted us to calculate V1 and V2, and these are the answers. Alright, my friends, this is all for exercise 11. Let's go to exercise 12. Now, my friends, let's go to exercise number 12. Find the values of the currents and the power delivered to the 24 ohms resistor. Okay, my friends, this is the exercise, but before going to the solution, let's understand this is the current I1, this is the current I2, and this is the 24 ohms resistor. We need to find the values of the currents and the power delivered to the resistor, okay? And to solve this, we are going to use a mesh equation. Let's write the mesh equations. Take a look at the loop of I1. There is going to be a voltage rise here. 25 volts is going to be equal to the voltage drops here. Okay? When I1 passes here, it causes a voltage drop. When I1 passes here, it causes a voltage drop. Alright? So it is 8 ohms plus 24 ohms times I1 minus 24 ohms times I2, okay? Because when I2 passes here, it also causes a voltage drop, but the voltage drop caused by I2 is in the opposite direction of the voltage drop caused by I1, alright? Because I1 goes downwards here and I2 goes upwards here. Did you understand? Now let's go to the loop of I2, okay? Let's go to the loop of I2. I have here 15 volts, okay? 15 volts is going to be equal to the voltage drop caused by I2 here plus the voltage drop caused by I2 there. It is going to be 24 ohms plus 16 ohms times I2 minus 24 ohms times I1. And again, when I2 passes here, it causes a voltage drop downwards here, but when I1 passes here, it causes a voltage drop pointing upwards, then they are reversed in the reverse direction. Alright, that's why I put this negative sign here. Okay, my friends, these are the equations, the mesh equations that describe the behavior of the current in this circuit. Alright, and we are going to simplify. Then it is easy to simplify, and when we simplify we find that it is 25 volts equal to 32 times I1 minus 24 times I2. And for this we find that it is 15 volts equal to 40 times I2 minus 24 times I1. Okay, my friends, these are the simplifications of these equations here. I'm gonna erase this part because I'm gonna need some room, because we will carry out other calculations. Alright, my friends? Alright, so from the first equation here, we discover that we are going to isolate, okay, we are going to isolate I2, okay, I'm gonna pass this to the other side. It becomes 24 times I2 equal to 32 times I1 minus 25 volts, okay? And if I pass this 24 dividing, I find that I2 is equal to 1.333 times I1 minus 1.041667, okay? And we are going to use this. We are going to use this value of I2 that we just found here. We are going to substitute it here to find the value of I1. Okay, applying the expression for I2 in this second equation here, we find that 15 volts is equal to 40. Let's follow there. 40 times I2, and I2 is this. 1.3333 times I1 minus 1.041167, okay, minus 24 times I1. Okay, my friends, now we have an expression with only one variable. The variable is I1. We can solve it, and if we conduct this mathematics, we find that I1 is equal to 1.932 amps. Okay, this is the value of I1. We already found the value of this current. We can take this value here and put in this expression here to find the value of I2. Using this, we find that I2 is equal to 1.534 amps. Okay, my friends, these are the values of the currents, okay? And how about the power delivered to the 24 ohms resistor? Okay, observe that I1 is greater than I2. The power is going to then be P is going to be equal to 24 ohms times the current squared. Okay, it's going to be I1 minus I2 squared. Okay, my friends, this is easy. You just subtract one from the other here in this way, and you square it, and then you multiply by the value of the resistance, and you find the power. I'm going to invite you to try it in your house, and you're gonna find the value of the power. Alright, my friends, and this is all for exercise 12. Let's go to exercise 13. Let's go to exercise 13 now, my friends. Use mesh currents to find the power delivered by the voltage source. Okay, the exercise wants us to use mesh currents to find the power delivered by the voltage source. Okay, my friends, this is the exercise. Let's go to the solution, and we are going to use mesh currents. First of all, let's consider the loop of I3. Okay, I3 passes here, here, and here. So it is going to be 5 ohms plus 15 ohms plus 25 ohms times I3 minus this resistor here. Observe this resistor here. I3 passes there and I1 passes there. They cause voltage drops in opposite directions. Then we find that it is 15 ohms times I1 minus, observe this resistor here, I3 passes in this direction, but I1 passes in that direction, and they cause voltage drops in opposite directions. That's why I put negative 25 ohms times I2 here, and this has got to be equal to 0. Okay, my friends, this is the loop of I3. Loop of I3. Similarly, we are going to proceed for this current here. Observe that we have a voltage source here. We are going to begin with the voltage source. 75 volts is equal to I1 passes here and here, okay? It is then 10 ohms plus 15 ohms times I1 minus, here we saw that I3 passes in that direction. It is minus 15 ohms times I3. And observe that we are considering the loop of I1 here at this moment, and I1 passes here in this direction, causing a voltage drop in this direction here. But I3 passes in this direction, causes a voltage drop in the opposite direction. That's why I put a negative sign here. Okay, my friends, and this is the loop of I1. Let's consider now the loop of I2 now. Here, observe that the current I1 was going in this direction here, but observe that the exercise shows that the loop of I2 is going to flow in this direction here. So it is not going to be like this, okay? It is going to be different. It is going to be this: 75 volts plus, because 75 volts plus 25 ohms plus 1 ohm times I2, and here I2 passes in this direction and I3 passes in the opposite direction, and I3 causes a voltage drop in the opposite direction, and then we write minus 25 ohms times I3. Okay, my friend, and this is equal to 0, and this is the loop of I2. We have described the mesh equations. We have written the currents in terms of resistances and the voltage. What we need to do now is to simplify. Then we're going to get the results and simplify and put in a way that is better for us to work with and visualize what's going on. Okay, I'm going to erase here for some room, and you are going to see the simplified version of these equations. Okay, my friends, then we have that it is 25 times I1 minus 15 times I3 equal to 75. Okay, 26 times I2 minus 25 times I3 equal to negative 75, and negative 15 I1 minus 25 I2 plus 45 I3 equal to 0. Okay, these are the mesh equations that describe the behavior of the circuit here. We have three equations with three variables. We can solve this problem, okay? The number of variables has to be equal to the number of equations to be solvable, okay? Using the first two equations, let's use the first two equations here, okay? I1, we relate I1 with I3 and I2 with I3. Let's use the first two equations and we're gonna see that I1 is equal to 15 times I3 plus 75 divided by 25. Okay? What did I do? What did I do? I passed this to this side, okay? Negative 15I3, I passed to the other side. It became 75 plus 15 times I3. And this 25 I passed divided to the other side and it became this. Okay, and if we divide, we find that I1 is equal to 0.6 times I3 plus 3. Okay, my friends, now we are going to do the same with the second equation. We're going to do this 26 I2 is going to be equal to 25 times I3 minus 75 divided by 26. What did I do? I passed this negative 25 times I3 to the other side. It became positive 25 times I3 minus 75, and this 26 multiplying I2, I passed to the other side dividing, and I got this, okay? And in this way, if we divide, we find that I2 is 0.961 times I3 minus 2.885, okay? And then we have both I1 and I2 described in terms of I3. What can we do now? We can substitute here. Instead of I1, we are going to have this expression in terms of I3, and here instead of I2, we are going to have this expression in terms of I3, okay? And we are going to have one equation in one variable, and the variable is I3. We are going to substitute, and we're going to find that negative 15 times I1. But I1, we discovered that it is 0.6 times I3 plus 3, okay, minus 25 times I2, and I2 we found it to be 0.961 times I3 minus 2.885 plus 45 times I3, and this is equal to 0. And in this way, okay, we have an equation with only one variable. We can calculate it, use simple mathematics, and we find that I3 is equal to negative 2.265 amps. Okay, my friends, this is the value of I3. Now that we know I3, we can substitute this value here, and we are going to find the value of I1. The same will be done for I2. We take this value, we substitute here, and we find the value for I2. Okay, substituting, we find that I1 is equal to 1.641 amps, and I2 is equal to negative 5.062 amps. Okay, my friends, these are the values of the currents. And lastly, the exercise wants us to find the power delivered by the voltage source. Okay, write this because I'm gonna have to clear the board to calculate the power delivered by the voltage source. Okay, my friends. The power delivered by the voltage source is equal to P, is going to be equal to the voltage of the voltage source times the current. I1, we observed that I1 is I1 minus I2, okay? I1 is in this direction, I2 in this direction, I1 minus I2, okay? I1 is in the positive direction and I2 is in the negative direction, okay? Then P is going to be 75 volts times I1 is 1.641 and I2 is negative 5.062, okay? And the current resulting from this is 6.703 amps and the power is 502.7 watts. And this is all the exercise we wanted us to calculate, my friends. I hope you understood everything. If not, you can go back to the beginning of the video to understand it, okay, and watch it again. Alright, my friends, this is all for exercise 13. Let's go to exercise 14. Exercise 14, my friends, find the Thevenin and Norton equivalent circuit for the circuit of the board. Okay, my friends, this is the exercise. Let's go to the solution. Let's understand what's going on here. The exercise wants us to take this circuit here and find the Thevenin and the Norton equivalent circuits, okay? And this is what we are going to do. Let's begin with the Thevenin's equivalent circuit, alright? The Thevenin equivalent circuit, we know that the Thevenin equivalent circuit is made up of a voltage source and an equivalent resistance here, okay? The open circuit voltage, and the equivalent resistance. This is the Thevenin equivalent circuit, okay? And this is what we are going to do. Firstly, we're going to find the open circuit voltage here. There is going to be a voltage here, okay? And we are going to calculate this open circuit voltage to calculate the Thevenin's equivalent circuit. Okay, my friends, to help us solve this, we'll use a voltage Vx. Let's use a voltage Vx here to help us calculate this. Firstly, we find the open circuit voltage. For the node Vx, we see that there is going to be a current. There is going to be a current entering here. I'm going to call it I1. There is going to be a voltage leaving this node here. I'm going to call it I2. And there is this current here that also enters the node, and I'm calling it I3, okay? And remember that the sum of the currents that enter a node have to be equal to the sum of the currents that leave the node. Okay, my friends, therefore, the currents that enter the node are I1 plus 1 amp, okay? I1 plus I3. These are the currents that enter the node, and the current that leaves the node is equal to I2, okay? As we don't know the value of the currents, we have to describe them in terms of voltage drops and resistances. Then, how do we describe I1? We describe I1 as 10 volts minus Vx divided by 10 ohms plus 1 amp, and this is equal to I2, and I2 is equal to Vx divided by 5 ohms. Alright, my friends, this is the node equation, okay, that we use to describe this, okay? And we are going to have to simplify it. We simply just need to simplify it. We have only one variable here, okay? When we have one equation, we need only one variable. If there were more than one variable, we would not be able to solve this equation. We can solve this equation because there is only one variable here, okay? And we are going to solve it for the value of Vx. So it is going to be 10 volts divided by 10 ohms minus Vx divided by 10 ohms plus 1 amp. This is equal to Vx divided by 5 ohms. Okay, this is simply mathematical manipulation, and from this we find that the value of Vx is equal to 6.67 volts. Okay, my friends, and observe that Vx is here. Alright, Vx is here. Vx is the very open circuit voltage. Then VOC is equal to 6.67 volts. Alright, my friends, this is how we calculate the open circuit voltage. What we need to do now is to calculate the equivalent resistance to complete the Thevenin's equivalent circuit. Okay, let's calculate then the equivalent resistance. The equivalent resistance is calculated by setting each of the forcing terms at rest. Okay, a voltage source at rest is a short circuit. Okay, and I'm going to repeat here the passive elements. And how about the current source? The current source at rest is an open circuit. So we just let it open here where there was the current source. Okay, and these are the points A and B. Alright, my friends, and this is the 5 ohms resistor, and this is the 10 ohms resistor, and observe that they are in parallel. They are in parallel. How do we know that they are in parallel? Because they share two nodes. This node is common to this and this, and this node here is common to this and this. When they share two nodes, we know that they are connected in parallel. So the equivalent resistance is going to be the parallel connection between these two resistances here, the 10 ohms resistor and the 5 ohms resistor. And how do we calculate the parallel connection? It is the product divided by the sum. Okay, the product divided by the sum, and if we calculate, we find 3.333 ohms. Okay, and my friends, this is precisely the equivalent resistance. The equivalent resistance that we want is to find is this. So we have here already our Thevenin's equivalent circuit, VOC. VOC we calculated and we found it to be 6.67 volts, and the equivalent resistance we found it to be 3.333 amps. Alright, my friends, we have already our Thevenin's equivalent circuit. What we need to do is to find the Norton equivalent circuit. Okay, and what is the Norton equivalent circuit? The Norton equivalent circuit is a current source, and in parallel here the equivalent resistance, and this is the short circuit current. Okay, this is the Norton equivalent circuit, and this is the Thevenin's equivalent circuit. Alright, my friends, and observe, this is a detail, observe that this is the same. The equivalent resistance for the Thevenin equivalent circuit is precisely equal to the equivalent resistance for the Norton equivalent circuit. Okay, my friends, we know that above the Norton and the Thevenin equivalent circuits, the resistance is the same. Okay, that's the equivalent resistance that serves for both the Norton and the Thevenin equivalent resistance circuit. Okay, and to calculate this, we don't need to use all this. We could have used all this to calculate the short circuit current here. What we would need to do is to simply short circuit here. Okay, we could simply short circuit here. Okay, we cause a short circuit here, and the short circuit current of the Norton equivalent circuit passes here. We could have done that, but this is not the technique that we are going to use. The technique that we are going to use is that the Norton current is the division between the Thevenin voltage by the equivalent resistance. Okay, this is an alternative way of calculating the short circuit current. We could have used this, but we are going to use this technique because it facilitates us in the case we are in an exam and we are short of time. We can simply do this and we find that it is 6.67 volts divided by 3.333 amps, and this is 2 amps. Okay, my friends, and this is the short circuit current of the Norton equivalent circuit, 2 amps. Okay, my friends, did you guys understand what I did? Alright, if not, return to the beginning of the video and watch it again, because this is important. This is important. The Norton and the Thevenin's equivalent circuits are very important in solving linear circuits. Okay, my friends, this is all for exercise 14. Let's go to exercise 15 now. Exercise number 15 now, my friends. Find the Thevenin and Norton equivalent circuits of the circuit on the board. Okay, my friends, this is similar to the previous exercise. We are going to find the Thevenin and the Norton equivalent circuits for this circuit here. Okay, let's begin with the Thevenin equivalent circuit. The Thevenin equivalent circuit requires us to calculate an open circuit voltage here. Okay, my friends, and one more time, this is the Thevenin equivalent circuit. We have here the open circuit voltage and here the equivalent resistance. Alright, this is the Thevenin equivalent circuit. And to help us calculate, we are going to use some labels here. I'm going to call this current here I1. I'm going to call this current here I2, and I'm going to call this current here I3. Okay, my friends, and observe that we have a node here. Okay, all right, can you see we have a node here, and for any given node the sum of the currents that enter the node have to be equal to the sum of the currents that leave the node. All right, my friends, then we know that I1 is equal to I2 plus I3. All right, my friends, okay, and observe also that no current goes to that direction because it is open here, so I3 can only pass here. All right, then we know already that I3 is equal to Ix. All right, this is how we are beginning solving this exercise. All right, my friends, and how about the value of I2? We know that the value of I2 is equal to 0.5 times Ix. Alright? Then, substituting this here, we know that I1 is equal to I2, 0.5 Ix plus I3, and I3 is Ix. And ultimately, we find that I1 is equal to 1.5 times Ix. Alright, my friends, this is the first step in solving this exercise. And knowing that I1 is equal to 1.5 times Ix, we can calculate as follows. Observe the voltage drops. Observe the voltage drops. 25 V is going to be equal to 5 ohms times I1 plus 10 ohms times I3 plus 10 ohms times Ix. Okay? Take a look at this. Take a look at this. Observe these voltage drops. Here we have one node here. We can regard this as the reference. We can regard this as the reference. From here to here we have a voltage. From here to here we have a voltage, and from here to here we have a voltage, okay? One more time, from here to here, from here to here, and from here to here, it has to be equal to this, because this is from here to here, okay? So, this voltage here, this is what I did here, this voltage here, okay, has to be equal to this voltage here, plus this voltage here, plus this voltage here, okay? Because they begin at the same reference and end at this node here, okay, my friends? And this is the equation that represents this voltage drops here and this voltage rise here, alright, my friends? And using this equation here, we're gonna find the value of Ix, okay? Remember that I1 is 1.5 Ix. Remember that I3 is Ix, and Ix is Ix. And manipulating this, it is easy, simple mathematics. We find that Ix is equal to 0.9091 amps. Okay, this is the value of Ix. But the exercise doesn't want us to calculate the value of Ix. The exercise wants us to go further and calculate the value of the open circuit voltage here. Okay, the open circuit voltage is going to be equal to the multiplication between 10 ohms and the value of Ix. The value of Ix, we found it here, okay? And if we calculate this times this, we find that the value of the open circuit voltage is 9.091 volts, okay? This is the value of the open circuit voltage. I'm going to write it here, okay? VOC is equal to 9.091 volts. I'm going to write it here to not forget, because I'm going to need room, and I'm going to have to erase it here. Alright, my friends, we are understanding everything. Okay, if not, you go back to the beginning of the video and watch it again. Alright, my friends, now let's go to the Norton. Let's go to the Norton equivalent circuit. Okay, let's go to the Norton equivalent circuit. The Norton equivalent circuit is going to be this. Let me erase here. Let me erase here. Okay, because we are not going to deal with the Thevenin equivalent circuit anymore. We are going to deal with the Norton equivalent circuit. Okay, and for the Norton, okay, this is not going to be open. We are going to short circuit here. We're going to have a short circuit here, and this is going to be the short circuit current here for the Norton. Alright? Alright? And observe here. Observe that this is similar to this and this is similar to this, okay? So, there is resistance here and there is a short circuit here. So the current is not gonna pass here, okay? Ix is equal to 0 because the current is going to flow entirely through the short circuit. It is not going to pass through this 10 ohms resistance. It's going to go directly, this is important, it's going to go directly to the short circuit. It's not going to pass here, and the conclusion that we get that in this case Ix is equal to 0. Okay? Observe that the short circuit is in parallel with the 10 ohms resistor, which means that Ix is equal to 0. And as Ix is equal to 0, we know that I2, observe here that I2 is equal to 0.5 times Ix, but we found that Ix is equal to 0. Then I2 is also equal to 0, or okay? Have you guys fully comprehended what I did there? Alright, thus the short circuit current is only the current flowing in the circuit, okay? The short circuit current is the only current flowing in the circuit, okay? It is going to go all the way down here. It is not going to pass here or here. It is going to go all the way there, okay? Then it is going to be 25 volts equal to 5 ohms plus 10 ohms times the short circuit current, okay? The short circuit current is going to flow all the way down there, alright? All the way down there. It is not going to go down here, it is not going to go down here. It's going to flow directly to the short circuit there. Did you understand? Okay? The short circuit current is going to go directly to the short circuit there. And if we carry out, we find that the short circuit current is 1.667 amps. Okay, my friends, this is the current of the Norton equivalent circuit. Remember that the Norton equivalent circuit is like this. We have the short circuit current, and in parallel here we have the equivalent resistance. Okay, and here are the outside terminals, and this is the short circuit current. Okay, my friends, lastly, with the values of the open circuit voltage and the short circuit current, we find the equivalent resistance. There is an alternative way, okay? We could have calculated the equivalent resistance in another way, but there is an alternative way which saves us a lot of time, which is to simply divide the equivalent resistance. Is going to be the division between the open circuit voltage and the short circuit current, and this is 9.091 volts divided by 1.667 amps, and this is equal to 5.45 ohms, okay? This is very straightforward, and I invite you to try to remember this, to memorize your exam, because instead of calculating all this, setting each of these terms to rest to calculate the equivalent resistance, there is this shortcut. If you remember that the equivalent resistance is simply the division between the open circuit voltage and the short circuit current, you are going to save a lot of time and find it quickly, okay, in this way. And with these values we can write the Norton and the Thevenin equivalent circuit. Okay, my friends, this is all for exercise 15. Let's go to the last exercise of this series, my friends. Let's go to exercise 16. Alright, my friends, let's go to the last exercise. Let's go to exercise 16. The exercise says, for the Wheatstone bridge of the figure with Vs equal to 10 volts, R1 equal to 10 kilo ohms, R2 equal to 10 kilo ohms, and Rx equal to 5,932 ohms. And if the detector, this is the detector, if the detector can be modeled as a 5 ohms resistor, letter A, what is the value of R3? What is the value of R3 required to balance the bridge? Okay, one more time. In letter A, what is the value of R3 required to balance the bridge? And letter B, suppose that R3 is 1 ohm higher than the value found in part A. What is the current through the detector? Okay, my friends, this is the question. Let's go to the solution. Let's begin with letter A. Let's suppose that Ig is equal to 0, okay? This is our first assumption. Let's suppose that Ig is equal to 0. There is no current flowing there. And in this way, we find that I1 is equal to I3, okay? I1 is equal to I3. Likewise, we find that I2 is equal to I4. Only when Ig is equal to 0. There is no current here. Then we know that this current is the same as this, and this current is the same as this. Okay? This is the first assumption. Alright? In this case, when Ig is equal to 0, we know also that the voltage VAB is equal to 0. Okay? If there is no current, there is no voltage drop. Alright? Then, okay, let's go see here. Let's observe this voltage here, okay? R1 times V1 plus this voltage here, VAB, have to be equal to this voltage here, okay? Okay? From this point to this point, it is VAB. From this point to this point, it is R1 V1, and this has to be equal to this, okay? They are the same voltage, but in different ways, okay? This has got to be equal to R2 times I2, okay? But we've found that VAB, when Ig is equal to 0, we've found that VAB is equal to 0, and as a consequence, we can write that R1 I1 is equal to R2 times I2, okay? Only when Ig is equal to 0, okay? And observe here that we found that I1 is equal to I3 and I2 is equal to I4, and in this way we find also that we were going to find that R3 times I3 is equal to Rx times I4, okay? Using the same reasoning that we used here, we would find this, but we are going to simplify it already, because we know that I3 is equal to I1 and I4 is equal to I2, and then we write here that R3 times I1 is equal to Rx times I4. Okay, my friends, this is one of the main results of this exercise, one of the main realizations that we needed to have to solve this. And gathering the results and manipulating, we find that R3 over R1 is equal to Rx over R2. Okay, this is only valid when the bridge is balanced, okay? When the bridge is balanced, that is when Ig is equal to 0, this is valid, okay? I'm going to erase it here because we are going to write other things on the board, but we must save this last result because it is important, okay? When the bridge is balanced, we have this proportionality here, okay? This holds true, alright? And now let's go to letter A. What did letter A want? Letter A wants us to find the value of R3 required to balance the bridge, okay? So, in letter A, we are going to use this equation here to find the value of R3 that balances the bridge, alright? And R3 is going to be equal to Rx times R1 divided by R2. we can simply use the values. Okay, Rx is this, R1 is this, and R2 is this, and when we use the values, we find that R3 is equal to 5,932 ohms. Okay, this is the value of R3 required to balance the bridge. And when the bridge is balanced, there is no current flowing through the central branch. Okay, my friends, this is the result of exercise of letter A. Let's go to letter B now. What does the letter B want? Suppose that R3 is 1 ohm higher than the value found in part A. What is the current through the detector? Okay, I'm going to erase here to calculate what we need for letter B. Okay, let's go slow because letter B is a little bit harder than letter A. Okay, we are going to need to use the Thevenin's equivalent circuit. Okay, we are going to have this here. Okay, and here. Okay, and there will be points A and B here. We are opening the circuit here. Okay, we are opening the circuit. And here is R1, R2, Rx, and R3. Okay, we will calculate the equivalent resistance. To calculate the equivalent resistance, we need to put the forcing term at rest. A voltage source at rest is a short circuit. Then there is going to be a short circuit here in the place of the voltage source. Alright, observe. Sometimes it is difficult to observe it here, but I'm going to draw it in a different way so you will be able to understand it in a different way. Observe this. This is terminal A, and connected to terminal A is R1 and R3. Okay? Okay? They are connected to terminal A, R1 and R3. Observe this, connected to terminal A is R1 and R3. Alright? And there is this loop here. I'm representing this entire thing here in this way. And connected to terminal B are R2 and Rx, alright? R2 and Rx. R2 and Rx. Okay, this is an alternative way of seeing this because sometimes it is difficult to see in this way. And if you redraw it in this way, maybe sometimes you're going to be able to see it in a better way. So what do we have? We have the parallel connection between R1 and R3 and the parallel connection between R2 and Rx. So the equivalent resistance, let's call it the equivalent resistance number 1, is going to be the parallel connection between R1 and R3, and the equivalent resistance number 2 is the parallel connection between R2 and Rx. Okay, and we are going to calculate this. We are going to calculate the equivalent resistance. From the parallel connection between R1 and R3, we are calling equivalent resistance number 1. And from the parallel connection between R2 and Rx, we are calling equivalent resistance number 2. And observe that they are in series. They are in series like this, okay? So this is equivalent resistance number 1, and this is equivalent resistance number 2, and this is terminal A, and this is terminal B, and they are in series, okay? Alright? We just need to use the values, okay? Here it is going to be R1 times R3 divided by R1 plus R3, and here R2 times Rx divided by R2 plus Rx. Okay, we simply use the values that the exercise gave. Okay, observe that R3 is 1 ohms higher. Okay, this is a condition of letter B. Letter B said that suppose that R3 is 1 times higher than the value found in part A. In part A, we found that R3 was equal to 5,932 ohms. Okay, and in letter B, we're gonna use that R3 is 5,933 ohms. Okay, this is the condition that the exercise imposed. Suppose that R3 is 1 ohms higher than the value found in part A. Yes, it has to be to unbalance, alright? Because when R3 is this, the value found in part A, there is no current here. Ig is 0 and the detector is detecting nothing. And we are going to unbalance the bridge by increasing R3 in 1 ohms, alright? And we are going to use this here, okay, to find the value of the equivalent resistance number 1, and R2 and Rx, we use the values, the original values, okay? And in this way we are going to have a total equivalent resistance, which is the series connection between these two, and this is 7,447 ohms. Okay, my friends, this is the equivalent resistance, the total equivalent resistance. The open circuit voltage is calculated as follows. We are going to calculate the open circuit voltage here. Let me erase here if you already understood. If you already understood how we calculate the equivalent resistance, the total equivalent resistance is this. If you already understood how to calculate this, I'm going to erase to calculate the open circuit voltage, because we are dealing with the Thevenin equivalent circuit, and the Thevenin equivalent circuit requires the equivalent requires the equivalent resistance and the open circuit voltage. I have here the source, okay, I have here the source, and observe here, let's call it VA here, okay, let's call it this VA, and let's call it this VB, okay. Observe that the VA is equal to R3 over R1 plus R3 times Vs. Vs is this, and observe that Vb is equal to Rx divided by R2 plus Rx times Vs, okay? And then the open circuit voltage VAB, the open circuit voltage VOC is going to be equal to VAB, which is equal to this minus this, okay, which is Vs R3 over R1 plus R3 minus Rx over Rx plus R2. Okay? So this is the open circuit voltage. All we need to do is to use the values. Vs is 10 volts, R3 is this here, the seventh value of R3, R1 is this, and R2 is this. We can simply use the values and we find that VOC is equal to 0.3939 millivolts. Okay, this is the value of the open circuit voltage. Alright, my friends, now that we already know the Thevenin's equivalent circuit, we are going to find the current of the detector. Okay, we are almost over. We are already calculating everything. We are almost over for this series. Okay, now we have the Thevenin's equivalent circuit. Okay, it is going to be VOC. We just calculated the value of VOC. We calculated the value of the equivalent resistance, and these are the points A and B. Okay, A and B, and here the resistance of the detector. Okay, R detector, and this, the exercise said, it is 5 ohms. Okay, and the current of the detector here, I detector, the current of the detector. To calculate the current of the detector, we can simply do this. I detector, the current of the detector is going to be VOC divided by the equivalent resistance that we calculated for the Thevenin's equivalent circuit plus the resistance of the detector. Sorry, I made a mistake here. It is not 5 ohms. Okay, it is 5 kilo ohms. Sorry, my bad, my friends. 5 kilo ohms. 5 kilo ohms. Okay, now everything is right. And the resistance of the detector. Okay, and if we use the values, we find that it is 393.9 times 10 to the negative 6 volts divided by the equivalent resistance, 7447 plus 5 kilo ohms. And in this way we finish the exercise by finding the value that the current of the detector is equal to 31.65 times 10 to the negative 9 amps. Okay, my friends, this is exercise 16. We have calculated everything, my friends, and this is the video that I wanted to make to show you how to solve purely resistive linear circuits. I am a teacher, my friends. If you want to book a lesson with me, use my WhatsApp number. Goodbye!